Well, hello again everybody. Now for some of you watching, I think you're going to find this video really pretty pointless because I'm not going to be fixing anything or repairing anything like I normally do. I'm actually just going to be entertaining myself for once. Now previously, I'm sure that some of you will remember that I visited an EMC test house, and just one of the many tests that they did was to look at how sensitive a piece of equipment was to electrostatic discharge. Now to do that test they actually used an electrostatic discharge gun, which is really quite a specialised piece of equipment, and I've got to admit that really caught my eye in that it's quite high voltage, a little bit dangerous, and it can actually be quite destructive and damaging. So all those things add up to being a lot of fun in my book. Now in the test lab, these ESD guns are actually quite expensive pieces of equipment, and the reason that they're so expensive is that, well, of course they're very specialised, but the actual high voltage output in terms of the actual voltage level and the rise time of the waveform, and in fact how the waveform decays as well, it's actually very, very tightly defined. Well, I'm not exactly going to be able to replicate that with what I build today, but certainly we can have a go and maybe make somewhat of an approximation of that, and I just think it'll be an interesting thing to do, so that's what I'm going to do. And so with this idea in mind, I've actually been thumbing through the eBay pages looking for various parts and components. So I've ordered some things like high voltage capacitors, we've got some high voltage step-up transformers and some high voltage rectifier diodes, and I'm hoping that we might be able to bodge those together to make something that at least works. So the first item that I bought is this, and at first glance it looks like a piece of porcelain, maybe just like I don't know, some kind of insulator or something like that, but they actually call this a doorknob capacitor, and this is probably one of the most important parts of my ESD gun that we're going to build. And the reason it's so important is that we're actually going to use this to store the high voltage charge before we actually discharge that high voltage into our victim. So these capacitors are really important because what this is actually meant to replicate, it's actually meant to represent a person, because again, as I said in the previous video, when you walk along on something like a nylon carpet, you charge up, you charge your whole body up. So what this capacitor is designed to do, it's meant to hold enough electrical charge to represent a human body. So we're going to charge this capacitor up with a source of high voltage, and then we're going to try and discharge it into our victim under test and see what happens. Now I think a lot of these doorknob capacitors are kind of like new old stock, and I think many of them come from places like Russia where they were used in stuff like radar equipment, because that works at high voltages. So I don't know if this is new or not. Certainly some of the terminals look a bit tarnished, but it's probably just that it's quite an old capacitor. Now I've got to admit, when you're buying stuff that's potentially old, we don't actually know whether this works or not, so I think we'd better just give it a quick test. Now apparently the maximum voltage that this capacitor is designed to work with, I think it's around 10,000 volts, and I think that the electrostatic discharge gun that we build, I think I'm going to probably maybe ramp the output voltage up to about 8,000 volts. Now when they're actually doing this electrostatic discharge testing for real, for many circuits 8,000 volts, that's the maximum that they go to, but I think it depends on the type of equipment that you're actually manufacturing. I think, for example, if you maybe make an equipment that works in a hospital, they actually, strangely enough, they have to do voltage discharge tests to, I think, really quite high voltages, because you know, places like hospitals, they are, you know, very warm and they're very dry, and you have you know, things like doctors walking around in nylon, you know, house coats, and you've got patients with bed sheets, and you can actually get very, very high voltages building up on people and equipment in an hospital environment. So I'm fairly sure that they actually do their testing at voltages considerably above 8,000 volts. But I think 8,000 volts is going to be enough for what I'm doing. So as I say, this one in theory is rated to about 10,000, and I think that this should be 100 picofarads. Okay, that's coming up as 98 picofarads, so I think that's actually close enough. I'll have that. Now I'm not sure if you'll actually be able to hear on camera, you may be able to, but the wind is actually absolutely roaring outside. We've been having some really bad storms here today, it's been really horrible. So I bought this little high voltage kit from eBay, and I think I paid about £3 for it, and I'm guessing that it was originally manufactured in China. Now I always do think it's amazing that how you can actually buy things like this for as little as £3, because you get quite a nice little clicky switch. We've got some form of power transistor. I don't even think it's got a number on it, so we've got an unbranded power transistor. I wonder if it's a real transistor or just a piece of plastic, I don't know. So we've got a transistor, we've got a diode, we've got a resistor, got a little heat sink and a circuit board, so all that's really quite cute. Of course we haven't got any instructions to build it, so we'll just have to wing it. So I still think it's quite amazing that you can acquire all these electronic goodies for just £3, so there's a lot of fun there. Of course the only problem is I now have to self-isolate myself for the next 15 days. So the reason that I bought these little high voltage generator kits is because they had these little transformers in them, and I thought that was a good thing to probably try experimenting with. So you can see here we've got it's a ferrite core transformer, so it's probably important to say that you can't just run these at 50 or 60 hertz. You can't run them with a sine wave. You've actually got to run them with something like quite a high frequency square wave, because the ferrite core won't work at low frequencies. Now the side that's got these red and the green wires coming off it, that's the secondary, that's the high voltage side, and I don't know if the camera will show up, but you can see maybe it's got lots and lots of very fine turns on it, very fine windings, so that's the high voltage output. And on the other side of the transformer, this is the primary side, and the primary side's got 4 wires on it. Now 2 of the wires are thicker than the others. 2 of the thick wires, they're actually what is used to energise the primary of the transformer, and then we've got 2 thinner wires. Now I forget what they call these thinner wires, but basically I think I would call them tertiary windings. So what these are used to do is these are actually used to provide feedback. These are feedback windings, and what they're used to do is they're used to turn on and off a transistor which is used to make the coil self-oscillate. So before I started to build this electronics kit, I've already gone ahead and I've actually painted this transformer really quite liberally in this conformal coating, and the reason that I've done that is because a lot of the windings were actually very, very loose and it felt like it was falling apart. So I actually thought that by putting some of this conformal coating on it, it would help just to mechanically stabilise everything. Now this is actually designed, this conformal coating, to be used at high voltages. It's actually designed for this type of application to stop the formation of corona and stuff like corona, I don't know. Stop the formation of well, corona. God, yes. Oh well. One of them days, isn't it? Right, okay, don't want to keep mentioning that. So I've gone ahead and I've already covered it in some varnish to help stop it, just falling apart, give it a bit more mechanical strength. And I think also what I'm going to do is I've got some of my my tape here, my Kapton tape, and I think I'm just going to go and try to put a few layers of tape around it as well. So I'm not necessarily putting this tape on for the high voltage insulation point of view. I'm just putting it on just to kind of mechanically strengthen everything, because it does feel as though all the windings, everything on it's quite loose. It feels as though it could all kind of just come apart. So I've just soldered a diode in, and I'm guessing that's probably going to be a flyback diode to actually protect the output transistor from the back EMF from the coil. So this is a resistor. I think it's 120 ohms according to the printed circuit board. Again, I've not looked at the circuit, but usually what the resistor is for is that these actual transistor oscillators, they're kind of self-oscillating. They do have a feedback winding, but you actually need something to actually get the transistor going into conduction in the first place. So you usually have something like a resistor to the plus supply, and then the transformer, the tertiary winding off the transformer, provides negative feedback, and that tends to turn the transistor off again when the magnetic core of the transformer starts to saturate. So it's a self-oscillating transformer. In fact, remember that when I was looking at that high pot tester it was just last week actually for me. Well, that also used a self-oscillating transformer arrangement. So I think we'll go ahead and just install all the easy components first. So I'm just going to stick in this little power switch. Really, it's quite cute, that little switch, and it was almost worth £3 on its own, that I think. Yeah, I've got to admit, the wind really does sound quite frightening out there at the moment. Right, so that's the switch and the diode and the resistor in. What shall we put in next? Ooh, big crack of thunder then. So if you actually do look on some websites where they actually show some information about ESD guns, it's tempting to think that all you've actually got in these things is a capacitor that we charge up, and then a resistor which is actually kind of to represent the amount of charge or limit the charge that can go through a human finger, etc. So it just looks like a capacitor and a resistor. But in fairness, if you were actually to buy one of these ESD guns, there's a lot more involved in them than that, because the actual discharge characteristic, the actual characteristic curve of the voltage discharge, it's actually very, very tightly defined under the standard. So although I'm having a go at building my own ESD gun, this isn't really going to be a particularly good representation of a commercially bought unit, but it's an interesting way to kill a really horrible wet Sunday. So the next part of assembling this is just a little bit tricky in that we've got all these windings coming out of the bottom of the transformer. I say all of them, there's only 4. There's actually the 2 main windings and the 2 thinner feedback windings, and it's not really very clear looking at the schematic or the circuit board how these actual windings go in. So I'm just kind of hoping that, well, I'm just trying to do it logically. If you get it wrong, if you get the phasing wrong, it won't actually work. So I guess you just take your chance really. So it looks like I've got to have 2 thick ones over there, a thin one, and got to join one of the thick windings to one of the thin windings. So I'm guessing that they go like that. Now I'm hoping that this enamel wiring is the stuff that is solder through, but we'll find out any moment now. Now I'm not sure if I said earlier, but this is definitely going to be kind of part 1 of the video, I think, because I'm not actually going to use this circuit board in the final ESD gun project. It's very unlikely I'm going to use it anyway. I'm actually just using this as a little bit of experiment because I wanted to know how good these transformers were that come with them. Now actually I also bought some other transformers. I've got one here which is well, it's slightly manufactured slightly differently. This one kind of looks better made, and it's kind of fully potted in some kind of clear resin. So I actually think that this will probably be a better transformer. But I just thought these kits were only £3, so I thought we'd give it a go and hook it up to the doorknob capacitor and, well, see if we can get it to chooch. Now I'm just taking an old sill header here, old single inline header. I'm just going to solder this onto the wires because it's quite important that we do have a way of generating a spark gap, because if you actually run this without some form of load on the output, you'll get a very high output voltage on this transformer. The problem is you'll get too high an output voltage, and what it'll do is it'll flash over the insulation, it'll damage it. So it is important to always have a spark gap so this transformer's got something that it can actually discharge into. Well, I guess we're ready to see if this thing will work, and well, I don't know. I suppose it'll work if the design's right. I don't think even I can get wrong. What is it? 1, 2, 3, 4, like a 4-component circuit, 1 transistor. Well, I'm sure if it's possible to get it wrong, I will do so. So I've got my power supply set to about 4 volts. Let's plug it in. Will it work? Well, there we go. So it's drawing actually more current than I thought. It's actually drawing about 1.5 amps, and the actual output transistor does get quite warm. Well, I've got to admit, that's not particularly exciting, is it? Let's see if we can do something to improve it. So of course it would actually be quite nice to measure the output from our little high voltage generator, but the problem is the output is AC, and it's not just that it's AC, it's high frequency AC. So although you've seen that I've got that large high voltage divider probe that I can plug into my fluke meter, even if I was doing that, the fluke meter would have problems with this high frequency waveform coming out of here. So I think we're going to have to do something else, and what that something else is I'm actually going to try to rectify this high voltage and then store it in this smoothing capacitor, and I suspect when we turn this on it should actually start to charge up the capacitor, and then this capacitor, when it actually discharges, it's going to go with a bit of a bang, it's going to go with a crack, because we're going to store quite a lot of energy up in here, or that's what I think will happen. I'm also going to go ahead, and I don't want this to charge up too rapidly, so I may end up taking this resistor out. I haven't done any kind of calculations, I've just pulled out a 10 meg resistor from the drawer because I just want to limit the well, I'm going to say limit the short circuit current. I'm sure that in theory even at 10 meg ohm it's probably still a relatively high current, but I don't think it's a bad idea just to have a bit of current limited in it. We probably should have a few of these resistors, but I'm just going to go ahead and give it a go. And I'm going to keep our spark gap, but I suspect this time if this charges up it's going to go with really quite a bit of a crack. Let's try it. This could be exciting, or maybe not. Well, nothing happened there, did it? Has that capacitor got any charge in it? I want something pokey. Oh, got a very little farty little discharge there. That was really quite unsatisfying, wasn't it? Wonder if it'll do anything more exciting if we just short out this resistor we've got here. So let's get rid of this 10 meg resistor. Well, that's a bit more pleasing, isn't it? Of course, now we have got a capacitor in here, we need to be really careful to keep everything discharged. Well, I'm afraid that was really quite distinctly uninteresting, wasn't it? But let's have a go and see if we can actually measure something using this high voltage probe now. I'm not sure if we'll be able to get a measurement out of it or not. Let's give it a go. And I think that we'll use this crappy Ryobi meter because I don't care if I actually blow the thing up. Okay, so at the moment this thing is, I'm getting actually 5 kilovolts out of it. Shall we see if we can get a little bit more? I'm just going to turn the voltage up a little bit. No, again it seems to be limited to about 5 kilovolts, this thing. Now one thing that is really important, I must keep remembering to discharge this capacitor because we can obviously build up quite nasty, dangerous voltages now we've got a capacitor. I haven't actually done the math on it yet. I don't know how many joules of energy is stored in here. I'll have to work that out in a minute. Well, I have to admit, I actually found that whole thing really quite disappointing. It's certainly not up to the sparky goodness. Do you remember the that high voltage ignition that I worked on of my friend Andy's truck? That thing was seriously evil. I'm a bit scared now. Some poo may come out. Oh dear, that is seriously violent. This is about as exciting as one of those piezoelectric grill starters, so it's fair to say that I'm fairly disappointed in this, and it needs some serious pepping up. Well, several electric shocks later and you can see that my circuit has grown somewhat. I think on my last measurements we were only really measuring around 5 or 6 kV output from this actual transformer, so you can see I've gone ahead and I've added some more components here, and what these two are, basically this capacitor and this diode, this is what they call a Villard doubler. Well, it does what the name says on the tin. Basically it will double the output voltage coming out of our transformer here. But the problem with these Villard doublers is they're kind of well known for producing an awful lot of ripple, and that isn't ideal for my little ESD test gun. I want to have a nice, smooth, well regulated output. What I've also got after that is we've actually just got some capacitance, and we've got a large resistor here, and it's not a particular value, it's just what came out of the junk box. It's about about 30 megohm, and the reason that I use that is because it's all out in the junk box. So what we've got is we've got 2 stages of smoothing here. And then this part of the circuit here represents what we would call the human part of the model. So here's a 50, again approximately a 50 megohm resistance here. And then we've got 350 ohms of resistance, which is kind of representing the discharge model, which I'm guessing is, you know, that's your finger. And then we've got the capacitor here, which is representing the whole charge in your body. So I'm hoping though that now we've actually got this voltage doubler in play, we're going to see a bit more output from here. But we have also got a little bit of current reduction coming into play by the way we're actually discharging it through this resistor network. Okay, that's enough waffle. Let me switch it on and show you. So you can see on the meter here we're actually getting about 11 kV. So it's done what it says on the tin. It's actually approximately doubled the output voltage from this. Now you can see it's sparking there, and that may not look very, very exciting, but we actually have got quite a lot of power stored up in this circuit, and I can actually just demonstrate that here. Well, as you just saw on the voltmeter here, we were getting around 10,000 volts of output from our little circuit here. Well, as you can see, if I just wanted to create a high voltage with this little circuit, that would be fine. But unfortunately, this little transformer here, due to its self-oscillating nature, it does actually create a problem for me. And that problem is that this actual transformer, this oscillator, it won't start up reliably if it hasn't got enough supply voltage, if it hasn't got enough power going to it. So that means that we can't actually turn the voltage generator down low enough. So what I'm going to do is I'm going to turn my power supply down now, and I'm going to try and start it up, and the problem is it isn't going to work. So as you can see now, I've just turned my power supply down to about 0.5 volts. But unfortunately my little transformer, it hasn't started up. So what I'm going to do is I'm just going to increase the voltage a bit. So I'm now at 0.85 volts. I'm going to switch the power back on. And again, unfortunately it hasn't started up. So what I'm going to do now is I'm just going to increase the voltage to 1 volt. So I've got the power supply set to 1 volt now. Turn the power back on. And we now come in, the oscillator's actually started up and it's outputting just under 3000 volts. Well, that's not really any good for what I want. I want to be able to control the output voltage very precisely. I want to turn it up and down. So what I'm going to do is I'm actually going to scrap this circuit, but it was just useful. It was a useful building block to play with this Vallard doubler and also this smoothing here, and just kind of see what these components do, because I don't really play about with high voltage that much. It was just an interesting little test board, this. So I think I've learned a lot playing with it, but what I think we need to do is we need to actually replace this voltage, this self-oscillating transformer, with something which I would call a little bit more conventional. So what I'm planning on doing is I'm going to build another little oscillator board, which is going to have a 555 timer in it and an output transistor, and the output transistor is going to feed our transformer here with a square wave. And then what we're going to be able to do is we're going to be able to vary the supply voltage to the transformer, so we should be able to have a very, very controllable output voltage, and we don't have to rely on this oscillator self-starting. So when I bought the high voltage goodies, I did go ahead and I bought a few different types of transformer off eBay. Now you can see that this one is fully potted, it's all encapsulated in resin, and I'm hoping that this one is going to perform a little bit better, because one thing that I noticed with that other transformer, it was giving off a really strong smell of ozone, like it was breaking down. So I don't really know how long it would last, but I'm hoping that this one is going to perform a little bit better. Now this one has only got 4 pins on it, so it's got kind of a conventional primary and secondary winding. It doesn't have this feedback winding. So as I say, what we're actually going to do is we're going to have to build an oscillator and a driver circuit to run this, because we can't make it self-oscillate.